Okay, good morning. In this session, I'm going to discuss about some examples on shear stress distribution across various sections. Numerical examples. First example, it reads out like this. A rectangular beam, 100 mm wide, 250 mm deep, is subjected to a maximum shear force of 50 kilonewtons. Determine the average shear stress, maximum shear stress, and shear stress at 25 mm above the neutral axis. So it is a simple example. It is a direct substitution in the formula. Okay, we know the expression for the shear stress, which is F(A)y bar by IB. This is general expression for any cross section, any shape. Okay, and for rectangular cross section, is neutral axis. General expression, if you consider d by 2 here, d by 2 at the bottom, and width is b. To find the shear stress at a distance y above the neutral axis. This is the expression, general expression actually. Here, this depth of shaded portion is d by 2 minus y. So area is d by 2 minus y into b. B is the width, which is constant here, and y bar is d by 2 plus y by 2. Yeah, we have seen this already. So a y bar will be f into d by 2 minus y into b into half into d by 2 plus y. This is a, this is y bar by ib. So here b cancels. We have f by 2i into d square by 4 minus y square. So this is the expression, specific particular case of a rectangular section. Okay, the shear stress distribution in rectangular section is given by this expression. General expression is here. Okay, we can use either one for finding out the shear stress at any distance y. Okay, yeah, coming to this problem, the average shear stress is given as tau average is shear force by area. Shear force is given here 50 kilonewtons. So converting it into newtons, and area 100, width, depth 250. So it will be 2 Newton per mm square. So average shear stress is 2 Newton per mm square. That's a direct substitution only. And maximum shear stress is 3 by 2 times average shear stress. This is the relation for maximum and average shear stresses in case of rectangular section. Okay, so it is 3 by 2 times of 2. average, that is 3 Newton per mm square. Okay, the maximum shear stress is 1.5 times average shear stress in case of rectangular section. Okay, now coming to the third part of the problem. Second part of the problem is maximum shear stress. First part is average shear stress. And third part of the problem is shear stress at any distance from neutral axis, at 25 mm from neutral axis. Okay. So this you can find out either by using general expression or by using particular specific expression formula for rectangular section. Okay, which is f by 2i into d square by 4 minus y square, where y is distance from neutral axis. So at any distance, by using this expression, you can find the shear stress. Okay. So in this, we substitute the values of shear force, moment of inertia, depth, and distance y to get the shear stress at that distance. Okay. So for now, at y equal to 25 mm, at y equal to 25 mm, what is tau? Okay. So for that, I you need to calculate, which is bd cube by 12. Okay. So tau is equal to f by 2 bd cube by 12 into d square by 4 minus y square. F by 2i into d square by 4 minus y square. Okay. That is, it comes out to be 6f by bd cube into d square by 4 minus y square. So substituting the values now, 6 into y is f is 50,000 newtons, b d cube into d square by 4, that is 250 square by 4 minus 25 square. Okay, so this is by calculating this, this comes out to be 2.88 Newton per mm square. So the shear stress distribution now is 0 at the extremes and maximum at neutral axis. At a distance of 25, it is 2.88 Newton per mm square, which is less than maximum. Which is less than maximum. Okay. So that's how we find out the shear stress at any distance. Okay. This is by using this expression, which is a particular for case of rectangular section. General equation also we can use to find this, which is tau is equal to f a y bar by I. General expression also we can use. Okay. So in which we find this. This is 25 mm and the remaining is 100. D by 2 is 125. Okay. And width is 100. Okay. So in this case, area is 100 into 100, 10,000. And y bar is distance of centroid of this shaded portion from neutral axis. In this case, it is 25 plus 50, 75. Okay. And width is 100 mm constant. I is equal to bd cube by 12, that is 100 into 250 cube by 12. Okay. 100 into 250 cube by 12. So it comes out to be 130.208 into 10 power 6 mm power 4. Okay. Yeah. Now substituting these values, you will get tau, which is 50,000 F value, and A is 10,000. Y bar 75 by 130.208 into 10 power 6 into 100. Yeah. This also gives the same value, 2.88 Newton per mm square. Okay. This is alternative formula, or general formula for finding out the shear stress at any distance. Okay. You can use any one, either this one or the particular case of rectangular section. You can use this. Okay. Both will give the same answer. Okay. So this is first example. Now let us see another example. It reads out like this. A timber beam of rectangular section is simply supported at the ends and carries a point load at the center of the beam. The maximum bending stress is 12 Newton per mm square and maximum shearing stress is 1 Newton per mm square. So find the ratio of span to the depth. So here the maximum bending stress, F, 12 Newton per mm square. Maximum shearing stress, tau, 1 Newton per mm square. Okay. It is a simply supported beam carrying a point load at the center. Simply supported beam carrying a point load at the center. Okay. So you have to find the ratio of L by D, span to depth. For this limiting conditions, you need to find span to depth ratio. Okay. So you need to find two ratios actually. One based on limiting bending stress. The second one based on limiting shear stress. Okay. Yeah. The least of these two will be the allowable span to depth ratio. Okay. So now let L be the span and W be the point load at mid span. So maximum bending moment is WL by 4. Maximum bending moment is WL by 4. And rectangular section, it is a rectangular section. So moment of inertia is BD cube by 12. BD cube by 12. And now the bending stress is given as M by I into Y maximum. Okay. That is WL by 4 divided by or into 12 by BD cube into D by 2. Okay. Yeah, that is F is given now 12. Okay. WL by 4. This is 6. So 3WL by 2 BD square. 3WL by 2 BD square is 12. Okay. Okay. Now, so from this, you will have W L by BD square is 8. W by BD into L by D. We can write this as W by BD into L by D is equal to 8. Now, coming to the second condition of tau maximum, which is given as 1 Newton per mm square, and maximum shear stress is also given as 3 by 2 into average shear stress. Average shear stress, we know it is F by BD. Okay, and F is the shear force, maximum shear force, which is W by 2. W by 2. Therefore, tau maximum is equal to 3 by 2 into W by 2 BD, or from this, and that is equal to 1 actually. Tau maximum is 1. So W by BD is equal to 4 by 3 from this. Now we substitute this value of W by 3 in the previous expression. Okay, W by BD into L by D. So W by BD, that is 4 by 3 into L by D is equal to 8, or L by D is equal to 8 into 3 by 4, that is 6. So this is the allowable ratio of span to depth. Allowable ratio of span to depth. Okay, that is what is asked in the problem. Find the ratio of span to depth so that it satisfies the conditions, given conditions. Another example, a simply supported wooden beam of span 1.3 meters having a cross section of 150 mm wide and 250 mm deep carries a point load W at the center. The permissible stresses are 7 Newton per mm square in bending and 1 Newton per mm square in shear. Calculate the safe load. Yeah, here we will find out safe load based on limiting bending stress and limiting shear stress. Okay, the least of the two will be the limiting safe load actually. Okay, so here when you consider this point load at the center, point load at the center, the span of the beam is 1.3 meters. Okay, 1.3 meters, having cross-sectional dimensions, that is breadth 150 and depth 250. Breadth 150 and depth 250 mm. Okay, so now the limiting bending stress is 7 Newton per mm square and limiting shear stress is 1 Newton per mm square. It is given. Okay, yeah. It is given. F is 7 Newton per mm square and tau is 1 Newton per mm square. Okay, now safe load W is calculated based on limiting bending stress F. Okay. Yeah. Now use this expression M by I is equal to F by Y. Okay. Yeah. From this bending moment is maximum bending moment WL by 4. Okay. Divided by or M is equal to F by M is equal to F by Y into I, or F into BD square by 6 actually, the section modulus. Okay. I by Y maximum. Y maximum is D by 2. So BD cube by 12 divided by D by 2. That is BD square by 6. Okay. So the limiting value of bending stress is 7 and width is 150. Depth is 250 square by 6. And span is 1.3 meters. So which gives W as 7 into 150 into 250 square by 6 into 1.3 into 4. Okay. So this comes out to be this comes out to be 250 into 250 into 150 into 7 into 4 divided by 6 divided by 1.3. It comes out to be 33.653 1.3 into 1000 here. Okay. Yeah. It comes out to be 33,653.85 newtons or 33.65 kilonewtons. So this is the load based on limiting bending stress. And based on limiting shear stress, tau is 3 by 2 into F by BD, where F is W by 2. The shear force is W by 2. So from this you will get W equal to 4 tau BD by 3. 4 into 1 into 100, 150 into 250 by 3. Okay. So 150 into 250 into 4 by 3. That gives 50,000 newtons or 50 kilonewtons. So the limiting value of W is the least of these two. That is least of this load and this load. Therefore, the safe load is equal to 33.65 kilonewtons. Safe load is least of these two loads. One is based on limiting shear stress, the other one is based on limiting bending stress. Okay. So the least of these two will be the safe load that can be applied. Let us stop here.
Like, share and subscribe. Hit the bell icon for more updates.